From brewing your morning coffee to purifying the water you drink, our world is filled with the constant, often invisible process of separating mixtures. But how do we choose the right method? How does a chemist isolate a single life-saving compound from the thousands of molecules in a plant extract? This isn't a process of guesswork, it's a systematic science. Today, we're going to explore the chemist's toolkit for taking things apart. We'll examine the most common and elegant techniques for separating mixtures, and you will see that every single method is based on one simple, powerful principle, utilizing the differences in the physical properties of the components. The key to separating any mixture, whether it's simple sand and water or a complex biological sample, is to identify a difference in the physical properties of its components. We are not performing chemical reactions or changing the identity of the substances. We are simply taking advantage of their innate characteristics, like their size, boiling point, solubility, or magnetic nature, to coax them apart. Let's start with the most intuitive method, filtration. This technique is designed to separate an insoluble solid from a liquid in a heterogeneous mixture. The physical property we're exploiting here is a difference in particle size. The process is straightforward. We pass the mixture through a porous medium, like filter paper. The pores in the paper are small enough to allow the liquid particles, the filtrate, to pass through, but they are too large for the solid particles, the residue, to fit. The solid is trapped and the separation is complete. The most common example of this is brewing coffee. The paper filter traps the solid coffee grounds while allowing the liquid, flavorful coffee to pass into your cup. The same principle is at work on a larger scale in municipal water treatment plants, which use large sand and gravel filters as a first step to remove sediment and solid impurities. What if the solid is completely dissolved in the liquid, forming a homogeneous mixture or solution? If you don't need to recover the liquid solvent, the simplest method is evaporation. This technique separates a soluble, non-volatile solid from a volatile liquid. The physical property we exploit is the massive difference in boiling points. By heating the solution, we give the liquid solvent molecules enough kinetic energy to overcome their intermolecular forces and escape into the gas phase or evaporate. The solid solute is non-volatile, meaning it has an extremely high boiling point, so it is left behind. This is precisely how sea salt is harvested from ocean water. The water is allowed to evaporate under the sun, leaving behind the crystalline salt. It's a simple yet powerful technique for isolating a dissolved solid. But what if you want to keep the liquid? Or what if you have a mixture of two different liquids? For this, we use a more sophisticated technique called distillation. Distillation separates components of a liquid mixture based on their differences in boiling point. Imagine a solution of salt water. We heat the mixture to the boiling point of water, 100 degrees Celsius. The water turns into steam, but the salt, with its much higher boiling point, remains behind. This steam then travels into a cooled glass tube called a condenser. The cool surface causes the steam to condense back into pure liquid water, now called the distillate, which drips into a separate collection flask. We have successfully separated and recovered both the pure water and the original salt. The same principle, when applied in a more complex form called fractional distillation, is the cornerstone of the entire oil industry, used to separate crude oil into gasoline, jet fuel, and other valuable components. For separating more complex mixtures, like the different pigments in a plant leaf or the various components of ink, we turn to an incredibly versatile technique called chromatography. The name literally means color writing. Chromatography separates substances based on differences in their solubility and their adhesion to a solid surface. In all forms of chromatography, there are two phases: a stationary phase like a piece of paper and a mobile phase, a solvent that moves through the paper. As the mobile phase moves, it carries the mixture with it. However, the components of the mixture will travel at different speeds. Substances that are more soluble in the mobile phase and less attracted to the stationary phase will travel farther and faster. This difference in speed is what causes the components to separate into distinct bands. It's a powerful analytical tool used everywhere from forensic labs to pharmaceutical research.